Here's a number that should stop you before we even start. Building a single leading-edge chip factory can cost more than the entire annual defense budget of most countries on Earth. Not the company, not the whole industry. One building. And here's the part that makes this genuinely strange, even by the standards of everything else we've covered in this series. You can spend that entire fortune, build the factory flawlessly, hire the best engineers alive, and still end up owning something worthless within a few years, not because you made a mistake, but because the technology underneath your feet moved on without you. Today we're going inside the most capital-intensive, most technically punishing, most geopolitically explosive business on the planet, the semiconductor fab. And by the end of this episode, you'll understand why the smartest players in this entire industry have spent decades figuring out how to make money from chips without ever actually owning one. Let's start with the number that defines everything else in this industry. A single leading-edge fab, the kind building chips at the 5-nanometer or 3-nanometer class, costs roughly $20 to $30 billion to construct, and some estimates for the very latest process nodes push toward $40 billion before a single chip has shipped. That's not a typo, and it's not the whole cost either. That figure is construction alone, before operating expenses, before research and development, before the inevitable next round of equipment upgrades that starts the moment the first one is finished. Think about what that actually means as a barrier to entry. This isn't a business you get into with ambition and a solid business plan. It's a business you can only enter with a checkbook the size of a national treasury, and even then, you haven't earned a single dollar yet. Every other business in this series eventually starts generating some revenue while it scales. A semiconductor fab sits there consuming tens of billions of dollars purely to reach the starting line, the moment it's finally allowed to attempt making a chip that someone might actually buy. Compare that to every other episode we've made. A coffee kiosk needs roughly $1 million to open its doors. A vineyard needs $250,000 at minimum, patient over a decade, but modest at the entry point. A fab needs $20 to $30 billion just to attempt the starting line, and then still has to prove it can actually make a working chip before a single dollar of revenue shows up. There is no other business in this entire series where the gap between opening the doors and trying to earn your first dollar is measured in tens of billions rather than mere months of operating losses. Here's where the story gets stranger. The real bottleneck in this industry isn't money at all, it's access to a single category of machine. Extreme ultraviolet lithography systems, built almost exclusively by one company, ASML, in the Netherlands, are required to print the finest features on the most advanced chips. Each one costs somewhere between $200 and $350 million, and here's the detail that should genuinely surprise you. Only a handful of customers on the entire planet are even permitted to buy the most advanced versions. ASML's production capacity is so constrained that who receives a machine, and when, effectively decides who gets to compete at the technological frontier at all. You can have all $30 billion sitting in the bank, ready to spend. If ASML doesn't have a machine to sell you this year, you simply don't get to play this round. Money alone doesn't buy your way to the front of that line, allocation does, and allocation is a decision made in the Netherlands, not in your boardroom. Here's the part of this industry that has no real parallel anywhere else in this series. A semiconductor fab has built-in technological obsolescence baked directly into its economics. You can run the factory flawlessly, perfect execution, disciplined operations, world-class engineering, and still watch it become economically irrelevant within a few years, simply because a newer manufacturing node or packaging technology made your entire plant obsolete. This isn't a hypothetical. Global Foundries spent billions developing a 7-nanometer process and building out the equipment to support it, and then simply abandoned the node entirely. Not because it failed technically. It worked. They abandoned it because once key customers shifted their business elsewhere, the future economics of continuing simply didn't work anymore. Imagine spending years and billions of dollars perfecting something that functions exactly as designed and walking away from it anyway because the math around it changed underneath you. That's not a failure of engineering. That's the specific, brutal risk profile of this entire industry. Most outsiders assume the semiconductor business is fundamentally about design, clever engineers drawing brilliant circuits. Insiders know the real formula behind profitability is something far less glamorous: yield, the percentage of chips coming off your production line that actually work. Here's why this number is so dangerous. A single percentage point change in yield at an advanced node can swing a fab's profits by hundreds of millions of dollars, turning what looked like a money machine into a loss generator almost overnight. The chips themselves, the design, the branding, none of that matters if your yield curve is wrong. This single number, quiet and unglamorous, is the actual lever separating a fab that prints money from one that burns it, and it operates almost entirely out of view of anyone who isn't running the factory floor themselves. This is precisely why the most valuable expertise inside a company like TSMC isn't necessarily the chip designers at all. It's the yield engineers, the people who spend years learning exactly how to nudge that percentage upward, batch after batch, on a specific process node. That expertise doesn't transfer cleanly from one fab to another, and it doesn't transfer cleanly from one node to the next node either. Every new process essentially starts the yield learning clock over from a lower number, which is exactly why the early months of any new node are the most financially dangerous period in the entire life of a fab. Here's a fact that should genuinely unsettle you about how this industry actually works day to day. At a brand new process node, it's common for 30 to 40% of the chips coming off the production line to be defective right out of the gate, sometimes more. And here's the brutal part: you pay full cost to manufacture every single one of them. Same silicon, same power, same cleanroom time, same hundreds of processing steps, whether the chip works or not. Only the good die, the chips that actually pass inspection, generate any revenue at all. Which means the early life yield curve on a brand new node essentially decides whether your entire multi-billion-dollar investment ever pays itself back. You can build the most advanced factory on the planet and still lose money for months or years while that yield curve slowly climbs, if it climbs at all, toward a level where the economics finally make sense. Building the fab is only the entry fee. Running it is its own enormous, continuous bill. A leading-edge fab burns somewhere between $5 and $8 billion per year in operating costs, and that's before you even count research and development or depreciation on top of it. That figure covers ultrapure water, specialty gases, industrial chemicals, round-the-clock staffing, constant maintenance, and a never-ending cycle of equipment upgrades that never really stops. Once you're in this business, you don't get to coast. You have to keep spending at this scale indefinitely, every single year, just to stay alive and competitive. Which means the $20 to $30 billion entry fee isn't really the finish line. It's just the down payment on an operating commitment that continues for as long as you're in the business at all. Here's a detail that shows just how unforgiving the manufacturing process itself actually is. A single 300mm silicon wafer typically passes through around 500 distinct processing steps, layers deposited, patterned, etched, and cleaned over and over in a precise sequence that can't be rushed or skipped. Imagine any other product that has to pass through 500 separate high-precision operations before it's finished, where a single mistake at any one of those steps can ruin the entire wafer, not just one chip, the entire disk full of them. That's not a worst-case scenario in this industry. That's Tuesday. 500 separate chances for something to go wrong, every single wafer, all day, every day, forever. The scale involved here is genuinely difficult to process intuitively, Advanced chips have features as small as 14 nanometers or below, thousands of times smaller than a grain of sand, and smaller than most viruses. And yet these microscopic features are patterned across an entire 300-millimeter silicon wafer, roughly the size of a dinner plate, which has to remain a nearly perfect crystal structure the entire time it's being blasted with plasmas, lasers, and extreme temperatures. You're simultaneously working at the scale of individual atoms and the scale of an object you could set a meal on, and both scales have to be perfect at once, across the entire surface, every single time, for the finished product to be worth anything at all. To make any of this possible, fabs operate cleanrooms that are stricter than hospital operating theaters, controlling airborne particles, humidity, and temperature to levels most people never encounter in their entire lives. A single microscopic dust particle landing in the wrong place can short multiple transistors simultaneously, destroying a chip that took months and enormous cost to bring to that point. Workers wear full protective suits, commonly called bunny suits, and the air itself is constantly filtered and recirculated. The environment surrounding the product isn't a supporting detail in this business. It genuinely is part of the product itself. Get the clean room wrong, and it doesn't matter how good your design or your equipment is. Given everything we've just covered, here's the twist that reshapes how you should think about the entire industry. Some of the most profitable companies in the semiconductor world don't own a single fab. NVIDIA, Apple, Qualcomm, AMD, all of them are what's called fabless. They design the chips, and they let companies like TSMC absorb the insane capital expense and the yield risk entirely. This model has enabled gross margins above 70% for some of these fabless giants, precisely because they don't own the factory carrying all the risk we've just spent this episode walking through. In effect, some of the most successful players in the entire chip industry have built their fortunes specifically by refusing to own a semiconductor fab in the literal sense, letting someone else carry the $20 billion checkbook and the 500-step manufacturing gauntlet while they focus purely on design. Which brings us to the company absorbing all of that risk on everyone else's behalf. TSMC controls over 90% of leading-edge logic chip production globally. But here's what most people miss. TSMC's real advantage isn't purely technical superiority. It's the business model itself, invented by founder Morris Chang, pure-play manufacturing, with no competing in-house chip designs of their own, so every single customer can trust TSMC not to steal or leverage their designs against them. Combine that structural trust with relentless yield learning compounded across decades and massive scale, and you get gross margins around 54%, a number competitors have struggled to match even after collectively spending hundreds of billions trying. The moat isn't just the machines or the cleanrooms. It's a business model built on being the one manufacturer every design house on Earth can trust with their most valuable secrets. Competitors haven't failed to match TSMC because they lack money or ambition. Samsung and Intel have both poured staggering sums into competing at the leading edge. What they've struggled to replicate is the decades of compounding yield knowledge and the specific trust relationship with fabless customers who worry, legitimately, about handing their most valuable designs to a manufacturer that might also be designing competing chips of its own. TSMC's decision, decades ago, to never compete with its own customers turns out to be worth more than any single piece of equipment in the building. Governments have poured billions into building domestic semiconductor capacity. Programs like the CHIPS Act are only the most visible example. But here's the detail that should genuinely change how you read every headline about this industry going forward. The company that most consistently profits from this entire subsidy boom often doesn't own a single fab at all. It's the equipment suppliers, ASML, Applied Materials, Lam Research, who sell the tools required to build any fab, anywhere to anyone. Governments around the world compete fiercely over who gets the next fab built on their soil. The equipment vendors, meanwhile, happily sell to literally every side of that competition simultaneously. Whoever wins the geopolitical fight over fab location, the same handful of equipment companies collect the invoice either way. The utility bills at this scale genuinely sound like typos the first time you see them. A large advanced fab can consume as much electricity and ultrapure water as a small city. Power for round-the-clock operation, vacuum pumps, chillers, and lithography systems that never really stop running, and enormous volumes of water used for cleaning wafers at every one of those 500 processing steps. An outage or a water shortage doesn't just inconvenience a fab. It can idle production entirely and cost millions of dollars per day in lost output. This is precisely why fabs routinely negotiate special utility arrangements directly with governments. At this scale, a fab isn't just a customer of the power grid and water system. It's a strategic partner those systems have to be built around. Here's the scale of demand sitting underneath all of this. In a single recent year, nearly 300 billion chips were sold globally, roughly 40 chips for every single person on the planet, including infants and the elderly who have never touched a computer in their lives. And that number has only grown since, pushed higher by AI servers, electric vehicles, connected devices, and data centers. And yet almost all of the actual value in that staggering volume concentrates into a tiny handful of companies, the ones that either own the very best fabs or own the best design and intellectual property instead. 40 chips per human on Earth, and the profit from nearly all of them flows through a number of companies you could count on your fingers. Beyond the famous Moore's Law, the observation that transistor density roughly doubles every 2 years, there's a lesser-known but equally brutal counterpart called Rock's Law. It states that the cost of building a fab roughly doubles every 4 years, which means the entire economic logic of this industry is a race against your own rising entry price, running at all times in the background of every strategic decision a fab owner makes. If your revenue and your technological progress can't keep pace with that doubling construction cost, you end up with something technically impressive and financially stranded. Exactly the trap that's caught several would-be competitors trying to chase TSMC over the decades. You're not just racing to build the next node. You're racing against the rising cost of building it at all. Even after clearing every other hurdle in this episode, the $30 billion, the ASML allocation, the yield curve, the operating costs, one risk remains that no amount of capital can solve directly. Over 90% of the world's most advanced chips flow through Taiwan. Any disruption there, a natural disaster, a blockade, a geopolitical conflict, instantly becomes a global technology crisis, not a regional one. Governments are trying to de-risk this by building fabs domestically in other countries, but replicating an entire ecosystem, the specialized suppliers, the decades of accumulated yield know-how, the trained workforce, turns out to be far harder than simply pouring concrete and installing machines. You can build the building. You can't quickly rebuild the decades of accumulated expertise sitting inside the people and processes that made the original ecosystem work. Recent efforts to build advanced fabs in the United States and Europe have run directly into this exact wall. The buildings go up on schedule. The machines get installed. What takes far longer, sometimes years longer than planned, is training a workforce to hit the yield rates that facilities in Taiwan achieve almost as a baseline, after decades of accumulated institutional knowledge that simply doesn't exist yet anywhere else. Geography in this industry isn't just about where the building sits. It's about where the expertise happened to accumulate first, and that kind of head start is nearly impossible to buy outright, no matter how large the subsidy check is. To make any of this possible at the cutting edge, modern fabs run processes like atomic layer deposition and atomic layer etching, adding or removing just a few atomic layers at a time, repeated across an entire wafer, over and over. Owning a semiconductor business today implicitly means running one of the most precise large-scale manufacturing operations humanity has ever built, and running it at full industrial volume, 24 hours a day, for years without interruption. Sit with that for a second. Atomic-level precision, operating continuously, at a scale that has to satisfy a demand curve of 40 chips for every person on Earth. There is no other industry on the planet operating at that specific intersection of precision and volume simultaneously. So here's the paradox this entire episode has been building toward. If your actual goal is economic upside from the semiconductor industry, the historically smartest answer has often been, don't build a fab at all. Own the intellectual property, the design tools, or the equipment instead. The companies that genuinely own the semiconductor economy in profit terms are frequently the ones sitting adjacent to the wafer rather than underneath it. The design software companies like Synopsys and Cadence, the core intellectual property licensors like ARM, and the equipment makers like ASML, Lam, and Applied Materials. They collect a toll from every single fab and every single design house on Earth, without ever carrying the yield risk or the technological obsolescence we spent this entire episode walking through, which ties directly back to the thread running through this whole series. From a coffee kiosk to a diamond mine to a football club to this, the most capital-intensive, most technically demanding business we've ever opened up. The thing everyone assumes is the asset almost never actually is. Here, of all places, that lesson reaches its most extreme form. The actual factory, the $20 billion building full of atomic precision machinery, is often the least profitable place to stand in the entire value chain. The real money sits just outside the cleanroom door, collecting a toll from everyone brave or foolish enough to walk through it. If this changed how you think about the chip inside your phone, subscribe, because we're just getting started pulling apart the businesses hiding behind the headlines. See you in the next one.